Hello everyone, thank you for coming to my talk. I'm Hajime, the data analyst at Mickey House, Japanese kids clothing brand. Today, I'll be speaking about causal inference with machine learning. So let's get started. This is the agenda for my talk. After a quick introduction, I will explain a background and concept of causal inference with machine learning. And then I will cover the use cases in business scenarios, meaning measuring treatment effects using meta-learners and Uplift modeling. After that, I will do a code through using CausalML. Just for the sake of time, please save your questions until the end. So just a quick introduction. Let me quickly introduce myself to explain my motivation behind this talk today. After graduating from Kyoto University with a master's in computer science, I was hired as a data analyst at Procter & Gamble, which is well known for its brand management and marketing capabilities. After that, I did some freelance and consulting work for some startup companies, and I relocated to New York, and I was hired as a data analyst at Mickey House, a Japanese kids clothing brand, looking to expand into the US market. I currently manage the e-commerce business and advertising. I believe today's topic is intriguing for Pydata audience because this technique has potential to enhance your company's marketing strategy and campaigns, resulting in sales incremental. From this presentation, my hope is that you will gain a basic understanding of causal inference with machine learning. Also, I hope this talk motivates you to try Uplift modeling in your environment. So, what is causal inference? Let's explain a common scenario. You are a data scientist, and you are helping your colleague who is in charge of marketing, and she says this: we sent coupons to some customers, and their purchase rate was twice as high as others. That means the coupon must have doubled the purchase rate. Do you think she's right? If it were me, I would say, congratulations, that's a great news, but may I ask who received the coupon? And then she says something like this: we sent coupons to customers who purchased within the last 12 months. Oh no, that's what I suspected. So what could the problem be? What we want to understand is the pure effect of the coupons. If we give coupons based on some intentional rules, we cannot compare the purchase rates apples to apples, right? Why is that? Customer who received the coupon might have made a purchase regardless of coupons. These customers might be more active, and they might have influenced by other marketing factors such as social media or newsletters. The effect of other factor is called selection bias. We can say a similar thing for digital advertising because current digital advertising techniques targets people who are more likely to convert. In this talk, we will discuss how to measure true effect of treatment and how to maximize marketing ROI. So, what is causal inference? Causal inference is the process of determining whether cause and effect relationship exists between treatment and outcomes. Traditionally, it has been used in the fields of marketing, healthcare, or marketing. For example, a famous case is determining whether a new medicine is effective or not in treating a disease. Here, using a medicine is called the treatment, and whether a patient recovers or not is called outcome. In e-commerce or marketing, we deal with treatments such as coupons, advertisements, or direct mails. What's the challenge of causal inference? The challenge of causal inference is we can only observe one outcome from the same customers, same individual. If time travel existed, we could use a coupon to a customer, then rewind time and observe what happens if we don't use a coupon to the same customer. However, in reality, we cannot do that, right? We can only observe one outcome from, we can only observe the outcome of one scenario from the same customer. So, causal inference involves simulating the scenario that didn't occur, which is known as counterfactual. Here, some of you might be wondering, why we don't just do an A/B test? Yes, A/B testing is the gold standard for measuring outcomes or making optimization. In the context of causal inference, it's called randomized control trials, RCT. So, I will refer to it RCT in this talk. Let's briefly explain this step with an example. First, we randomly divide customers into treatment groups and control groups. And then the treatment group receives a coupon. For example, let's say the purchase rate is like 40%. And then the control group does not receive a coupon. And the purchase rate is, let's say, 20%. In this case, the difference in conversion rate is 20 points. That's the effect of coupon. The key point of an RCT is to randomly assign customers into two groups. These steps ensure that the factors other than coupons are unbiased between the groups. So, okay. So if we understand RCT, does that mean everything is perfect? Unfortunately, no. Despite its simplicity and robustness, we often face situations where RCT can't be used. For example, your CEO may say, your mission is to maximize sales, not analysis itself. And your boss might say, I can't wait much longer to reach a conclusion. And sales team might say, this campaign involves external stakeholders, so it's hard for me to convince them to run RCT. So that's very common, right? So in this scenario, we cannot use RCT. So let's go through these challenges one by one. The first challenge is opportunity loss. With an RCT, half of the customer do not receive the treatment, potentially resulting in opportunity loss. The second challenge is time. Conducting an RCT may require waiting weeks or months to get a result. And also, RCT is hard when we involve external stakeholders, because sometimes client may not be capable of executing RCT. That's the reason why we need to use causal inference to measure reliable causal effects. So, when we cannot conduct an RCT, we need to use observed data. But observed data can be tricky as well. For example, take a look at this graph. This example is from the famous book, The Book of Why by Julia Paul. The x-axis shows the amount of exercise, and the y-axis represents the cholesterol levels. At the first glance, the graph seems to indicate that people who exercise more have higher cholesterol levels. However, this doesn't make sense based on common sense, right? Here, there is a factor we overlooked. It's age. The graph on the left is same as the previous one. But the graph on the right breaks down the data point into by the age group. When considering age, we see that people who exercise more tend to have lower cholesterol levels. This situation is known as Simpson's paradox because overall trend differs from the trends within subgroups. In this paradox, age was a confounding variable that affects both exercise which is a treatment, and cholesterol levels, which is an outcome. So in causal inference, it's crucial to account for and control this confounding variable. So I have already gone over the key concept of causal inference, so I would like to talk a little about causal inference with machine learning next. In recent years, algorithms combining causal inference and machine learning have been a hot topic. Today, for simplicity, I'll use the term causal machine learning to refer to causal inference with machine learning. Let's take a look at the history. From the 1970s to 1990s, researchers like Julia Paul and Donald Rubin established the foundation of causal inference. And as you might know, in 2000s, machine learning technology has evolved rapidly with the increase in data volume. And in 2010, and around 2010, the fusion of causal inference and machine learning began. And in 2019, user-friendly libraries such as CausalML or EconML were released. Compared to traditional causal inference, what are the advantages of causal machine learning? Simply put, it can manage more complex, more high-dimensional data at the individual level. So here, you might be wondering, why should we use causal machine learning, even though normal machine learning already offers a high predictive accuracy? It's because the objectives of normal machine learning and causal machine learning is completely different. So traditional machine learning focuses on prediction based on correlation. For example, traditional machine learning model tries to answer what will the customer buy next and what's the probability of that. On the other hand, causal machine learning aims to answer the question like, did the coupon increase sales? So also, the variables used are different. In normal machine learning, coupon availability is just one of the features, right? But in causal machine learning, coupon availability is called treatment variable. And this is very important because the goal of causal machine learning is to identify how this treatment variable affects the outcome, such as health. Now, we are going to look at two cases where we can use causal machine learning. The first one is measuring treatment effects using meta-learner, and the second one is uplift modeling. In the next section, I will explain each of these methods in detail. So, the first case is measuring treatment effects. By the way, what is a treatment effect? Conceptually, it's very simple. For example, if the potential purchase rate with the treatment is 20%, and the potential purchase rate without the treatment is 10%, then the treatment effect is 10%, 20 minus 10. That's very easy. This concept is known as the potential outcomes framework, developed by Donald Rubin. Let me briefly explain some notation here. If a coupon is given, we set z equal 1. And if no coupon is given, we set z equals 0. And the outcome with the coupon is shown as y1. And the outcome without the coupon is shown as y0. Now that we understand what a treatment effect is, so let's explore the different types of treatment effects we will discuss today. Roughly speaking, there are four. The most common metric is the average treatment effect, ATE, which measures the effect across all the customers. In traditional causal machine learning, the focus was this ATE. However, the approach does not consider the diversity or heterogeneity of the customers. In causal machine learning, we focus more on customer segmentation or customer targeting or personalization. So metrics such as CATE, conditional average treatment effect, or ITE, individual treatment effect, are used for this purpose. The conditional average treatment effect, CATE, measures the effect within specific customer segments, such as CATE for males, CATE for female, or CATE for people in their 30s. The individual treatment effect measures the effect at the individual level. Now, let's move on to how we can calculate these treatment effects using sample data here. Let's consider this question. Did a coupon increase sales? The data includes different customers with their attributes such as age, gender, and location. And the data also has the information Z, which is treatment, such as coupon, and Y, which is outcome, such as sales flag. Here, the column Y1 represents the outcome with the treatment. Also, the column Y0 represents the outcome without the treatment. If we know both of these columns, we can simply calculate the treatment effect by subtracting these numbers. However, the challenge is we can only observe one outcome from the same individual. To address this challenge, we can use a method called meta-learners. Here, we use machine learning to predict these counterfactual values, missing values. Meta-learners are techniques designed to estimate treatment effects by using machine learning models to handle unobserved data. Take a look at this table. The red text indicates numbers that were originally missing. But we have now predicted and filled in these numbers. And then we are now able to get the individual treatment effect, ITE. Now let's explore the different types of meta-learners here. Roughly speaking, there are 4 major methods: S-learner, T-learner, X-learner, and O-learner. S-learner is a simple approach, the most simple approach, and the O-learner is the most complex but provides more robust results. Today, I will discuss 2 of these methods, S-learner and T-learner. As S-learner stands for single learner, it uses only a single machine learning model. Look at this table. The S-learner uses all the available data to train a single model and then predict outcomes for both treated or non-treated customers. Next, let's look at the pseudocode to see how this approach works. This is very simple. By looking at the pseudocode, you can see how simple this approach is. We train the model using age, gender, location, and treatment as X, sales as Y. Then we use the model to predict the potential outcomes with and without the treatment. The difference between the outcomes is the treatment effect. Here, I use XGBoost, but you can also use GBM or random forest or other techniques. Now let's move on to the T-learner. T in T-learner stands for 2. Again, look at this table. This time, we split the data into treated customers and untreated customers. Then we train separate models for each group. This allows the model to better calculate the differences in responses between treated customers and non-treated customers. Let's look at the pseudocode to understand more. This is the pseudocode for T-learner. We split the training data into treated groups and treated group and a control group, and train the separate model for each group. Model underscore treated shows the shown in blue, predicts responses when the coupon is given, and the model underscore control, shown in red, predicts the responses when the coupon is not given. Here, let's return to this slide to discuss the other types of meta-learners. Compared to the S-learner and T-learner, the X-learner and O-learner are slightly more complex. But they are the advanced version of T-learner, so the concept is same. X-learner is ideal for handling heterogeneity treatment effect and imbalanced sample data for handling because it uses propensity scoring. O-learner is the best for high-dimensional data because it uses residuals to isolate the treatment effect from the confounding factors. Due to the time constraint, I won't deep dive into this, but if you are interested in learning more, I will recommend a good book at the end of this presentation. Next, let's talk about the second use case, uplift modeling. The key question is, who should we target to maximize sales? Uplift modeling helps to identify customers who are influenced positively by marketing offers. This is especially useful for cost-intensive marketing. For example, sending a newsletter is very cheap, so it's okay to send it to everyone. However, direct mails, free samples, or SMS notifications require higher costs, right? So in addition, when customers use coupons, profit will decrease accordingly. So in that case, marketers usually work with a limited budget. So Uplift model can help them to increase the ROI of the campaign. Now let's take a closer look at the customers to be targeted here. We can categorize the customer into one of four types. Persuadable are the people who might buy a product only if they are treated, only if they receive a coupon. And they are the main targets of Uplift modeling. This is a top left segment. Sure things are the people who will definitely buy your product, whether treated or not. And lost causes are people who will never buy your product, even if treated. And the last one, sleeping dogs, are rare customers, and they are less likely to purchase if they receive a treatment, which is a very rare case. Here, we don't need to give coupons to sure things, lost causes, and sleeping dogs, because coupons do not positively influence to those customers. There are two methods for Uplift modeling. The first method is a meta-learner approach, which I introduced earlier. The second one is decision tree-based method. This approach is a type of decision tree, especially designed for Uplift modeling. There are several variations, such as Uplift tree or Uplift random forest, but the key concept is the same. The advantage of this method is that it supports multiple treatment. That means instead of just testing only one coupon, you can compare the result of coupon A, coupon B, and coupon C to determine which coupon is the most effective to each customer. That is very practical. Additionally, this method supports the feature importance, helping to identify which variables are important. So let me introduce a key concept of this algorithm, Uplift tree algorithm. To explain the Uplift tree, I will compare it with a traditional decision tree. The goal of traditional decision tree is on the left. The traditional one is on the left, and the Uplift tree is on the right. the goal of decision tree is prediction. For example, the traditional decision tree tries to answer will the customer make a purchase? On the other hand, an uplift tree tackles causal questions such as who should we give coupons to? And now let me explain each method in detail. So let's start with the traditional decision tree. First, the decision tree tries to answer will the customer make a purchase? However, depending on how decision nodes are selected, there are many different ways to construct this tree, right? We can use customer attributes such as age, location, or gender for this split criteria. Here, how can we choose a better decision tree to construct a better decision node? On the left, there are two decision nodes here. On the left, the split is based on age, and on the right, the split is based on location. The black icon represents purchasers, and the white icon represents a non-purchaser. So which tree provides a better split? Long story short, the answer is the right one. Because in the left tree, purchasers and non-purchasers are mixed. On the other hand, on the right tree, purchasers and non-purchasers are clearly separated. Therefore, the right tree is a better decision. So, how can we quantify this judgment? For split criteria, Gini impurity used for this for traditional decision tree. Gini impurity can be calculated like this formula. Here, the left tree has the impurity of 0.44, while the right tree has a Gini impurity of 0. So using this metric, we can decide which tree is better which tree is better to split the customers. Next, let's consider the uplift tree. So the concept is this. Due to the time constraint, I skipped this detailed calculation, but this is the process, the calculation process for the left tree and right tree. And next, let's consider uplift tree. The concept is very similar, but this time we consider both the treated group and the non-treated group separately. Here you can see two uplift trees. The left one is based on age, and the right one is based on location. And in this case as well, the right tree is a better uplift tree. Why? So simply speaking, the left tree, on the left tree, purchasers and non-purchasers are mixed. On the other hand, on the right tree, purchasers and non-purchasers are clearly separated. Then, how can we quantify this split? So this time, for split criteria, squared Euclidean distance is used. We can also use divergence metrics such as KL divergence or other methods. But using this metric, the left tree has the distance of 1, while on the right tree, the distance is 4. So therefore, we can determine the right tree has a larger divergence. In other words, the right tree maximizes the uplift, meaning the difference in purchase rate between the treatment group and control group. So due to the time constraint, I will skip this slide, but this is a detailed calculation of the left tree and right tree. So let me proceed with coding part. Here, let me introduce two great OSS libraries. The first one is CausalML, which I will introduce later, and the second one is EcoML. The CausalML is mainly developed by Uber. Both of them are open sourced, and the CausalML is developed by Uber, and EcoML is mainly developed by Microsoft. And the most significant difference is that CausalML is focusing on marketing use cases or targeting use cases, while EconML is particularly strong in economics. I'll conduct a quick walkthrough using CausalML because it's straightforward in my case. In this code walkthrough, I will focus on explaining the core parts of the code, but this is you can check the full code with this QR code or this URL. Also, you can find this link from my Pydata schedule page. So first, we will need to import CausalML and other libraries. And today, I will use a Criteo dataset. Criteo is a famous advertising company. To fetch the Criteo dataset, I use skdiff library because it provides an easy function to download it. And this is key figures of the dataset. This data includes a user with, this data contains 13 million users, and the treatment, but the data set is largely imbalanced. Around 85% were treated users who saw the ads, while only 15% were non-treated who didn't see the ads. So let's review the conversion rate in each group. For the treatment group, the conversion rate was 0.31%. On the other hand, for the control group, the conversion rate was 0.19%. So what's the effect of advertisement of this data set? Can we simply subtract these numbers? No, as I have explained in this talk, the simple subtraction is incorrect because current digital advertising targets people who are more likely to convert. Now, let's use the meta-learners to calculate the average treatment effect, ATE. So CausalML provides a preset model called XGBT regressor. This model is an XGBoost in the T-learner framework. Using this method, the estimated ATE is 0.1%. This number is slightly lower than the simple aggregation result. Next, let's visualize the relationship between ATE and selection bias here. The difference is in conversion rate between control group and treatment group can be broken down into ATE, true effect, and selection bias. Next, after splitting let's do the uplift modeling. After splitting the data into train set and the test set, we use the uplift random forest to train the model. As you can see, the interface of CausalML is very similar to that of other ML libraries such as scikit-learn. We can train the model using the fit function, and we can predict the uplift result directly using the fit function. Also, we can display the feature importance. The features are masked in this data set, but we can see which features are important to decide this model. Here, it might be too detailed, but CausalML can visualize a tree structure. Also, this is a preparation for evaluation. We need to create the data set, a data frame, with these three columns, treated, conversion, and uplift for the next step. So this is an evaluation. So this is called the uplift curve. And let's understand the total cumulative gain. So this graph shows us how effectively our model can target users who are most likely to convert when we target that users. The light blue curve represents the uplift modeling approach, while the blue curve shows a random approach for comparison. In this case, the important point is just targeting just 20% can, just 20% of the total population can achieve 80% of the total results as if we targeted everyone. The x-axis represents the population, and the y-axis shows the total cumulative gain. The area under the the orange zone, the area between the two lines is called AUUC, area under the uplift curve. So AUUC is a metric used to evaluate the performance of this modeling, and the concept is similar to AUC, area under the ROC curve, and if an AUUC near 1 is better, and while the score near like 0.5 means it's no better than like guessing randomly. So this is a final step of this like uplift modeling. This code tries to extract the list of customers with the like priority uplift. So this So the summary, I've introduced the causal inference with machine learning technique, and please be careful about the like selection bias and confounding variables when you do this kind of modeling. And I've also covered meta-learners and uplift modeling. And if you are new to uplift modeling, CausalML is a good first step. Here are some links from my talk today. And please feel free to contact me via like email or LinkedIn. So thank you for your time, and if you have any questions or comments, I'll be happy to answer them. And also, how many?
We have time for 1 or 2 questions.
Okay. But anyway, I will wait here outside the room, so please feel free to reach out to me anytime after this session offline.